The one thing that's not listed in her bio in the package you received, that's actually the most important thing, is that she just received tenure at Harvard. Which, at Harvard, that's the academic equivalent of climbing Mount Everest, except it's actually more difficult than climbing Mount Everest. So I'll turn you over to Karin for her talk on exoplanets.
Well, thank you so much, both for the introduction and for your enthusiasm for the last week's event. It was a great way to start Holy Week Monday to at 6 a.m. get the message that I had been awarded tenure. Then, of course, I had to wait for another 6 days to properly celebrate, but it was worth the wait. So, what I want to talk about to you is a very specific kind of exoplanets, and those are the exoplanets that we would term habitable. And I'll go into what we mean with habitable. Now, my sort of real professional expertise is not really in the detection and characterization of these planets, but in how they're formed and how they get the characteristics they have. But still, I feel I can talk a little bit about exoplanets to you with some professional credibility. When I do get into more, let's say, the metaphysical speculations or like some thoughts that I have there, I am definitely speaking to you as a laywoman, and I am very happy to see that we have so many priests and theologians in the audience that can help me to, stray into heresy. So please do correct me if I do. But with that, so the title, on the origins and prevalence of habitable worlds. So when astronomers talk about habitable worlds or habitable planets, they mean something quite specific. And we can definitely, I'm going to leave plenty of room for questions. We can definitely talk about whether this is a reasonable way to define habitable worlds, the one we're using. What we mean is something that's not too different from the Earth. It's a rocky planet sitting at a distance from the sun where there's a good chance that you will have liquid water. And that's it. That's typically what we mean with a habitable world. Now, this has been mostly applied to thinking about exoplanets, and that's also where I will be spending most of my time. But I think it's important to keep in mind that there are actually places like that in the solar system that is not the Earth. That we are not the only habitable planet, or at least habitable place, in the solar system based on this very sort of basic criteria. In addition to the Earth, we do have planets with liquid water, or at least moons with liquid water in the solar system. Moons like Europa around Jupiter and Enceladus around Saturn are known to have water. And I think it's a travesty that we have not gone there and checked out if they have life as well, even if it's just bacterial life. I would actually argue that we don't know whether there's going to be even a plenitude of bacterial life in the universe, because we don't know how life originated here on Earth. And until we know that, it's very difficult to say what the probability is that it will arise somewhere else, given some specific conditions. And having a few more data points, even if they are within the solar system, would just be amazing. But I'll spend my time talking about exoplanets instead. And the one that I'll come back to a little bit because it was so amazing is the discovery of this Trappist 1 system that happened very recently, which had 7 planets around a single low mass star, with 3 of those planets being so-called habitable. But before going in, so I'll spend most of my time talking about the science of this. But there are a few questions that I think in this, especially for this audience, it's good to have in the back of your mind as we are talking or thinking about this. Which really boils down, if there is anything from this research that could actually be used to enrich our understanding of God, enrich theology. If we believe, at least with the medievalists, and I think also some moderns, that God does express himself through his creation, what does it mean if this creation is full of habitable worlds and potentially inhabited worlds versus the opposite? I think something that has really happened with the advent of exoplanet research is that we have gone from looking at the night sky. I mean, we see something, we've always seen something that's incredibly beautiful, and in some sense could, I think, be thought of and had been thought of as manifesting the beauty and the immensity of God, but still something that's vast and cold, and both in a literal and I think in a poetic sense, to something that's a bit more cozy. When we look up now at the night sky, I mean, we shouldn't just think about it as stars, but each of those stars potentially being a small world of its own, surrounded by planets of its own. So this is, I mean, the thought that is haunting me is thinking about what does this say about the Creator, this shift. It is a certain cosmological shift in the sense that the world that we look up on, the world we inhabit, looks quite different after the discovery of this very vast multitude of planets in our galaxy, and the realization that many of them will be habitable from this very basic criteria, and there is a good chance, there is a good hope that some of them will be inhabited. Now, when we think about exoplanets, I said this is something that is unfolding right now, this discovery of exoplanets and the characterization of exoplanets. Planets outside of the solar system have only been known for a couple of decades. So what this plot shows here is the number of new planets per year. So first of all, we haven't actually seen planets outside of the solar system for a very long time. This is something new. But what really stands out on this plot is what's going on over here, right? So in the past few years, we have gone from knowing about hundreds of extrasolar planets to thousands. And this is all thanks to a single space mission, Kepler, which is really responsible. These two big peaks here were the big two data dumps coming from this spacecraft, Kepler, in terms of new planets. So when we look at what these planets look like, they're not very similar to that nice Earth-like habitable planet that we want, at least not most of them. The first ones that were discovered, so we're going back here, were all quite weird from a solar system point of view. They were Jupiter-sized planets orbiting very close to their star. This is not something that we have in the solar system, so the very first thing we discovered is that, well, we might not be special in the sense that we are the only place where there's planets around a star, but we're not typical either. And that's something that has been reinforced as we're discovering more and more planets. The typical exoplanetary system does not look anything like the system we have here around our sun. The typical extrasolar system has what's called super Earths, and a bunch of them fairly close to their stars. These are sort of blown up Earths or smaller versions of Neptune, dependent on how we think they form. So among all of these planets, the ones that I want to focus on are the ones that are so-called habitable. And they only constitute 5 to 10 of these thousands of planets. Now, that does not mean that there are only 5 to 10 habitable planets in our neighborhood. Rather, what it means is that these are quite difficult to discover, and that this mission was set up to just be able to detect a few during the lifetime of the mission. So actually what we know, based on this mission, from these sort of 5 to 10 detections that I'm talking about, is that between 10 and 20% of all the stars in the galaxy have a planet in their habitable zone, or a habitable planet around them. The vast majority of those planets reside around very small stars, so-called M-dwarfs. So these are stars that are 10, 20% of the mass of our sun, so they're very dim compared to our sun. But that's where we find most of these habitable planets, are around these very, very small stars. And I think the most spectacular evidence for that, I'll come back to this in a second. Actually, no. So the most spectacular evidence for that was this discovery of the Trappist system that I showed on the front slide. So I just want to spend like a minute explaining how these discoveries are made. And it's going to be important when we think about how we can go further and actually characterize what these planets look like. So there are several different ways in which exoplanets are discovered, but the one that Kepler uses is in some sense the easiest and most straightforward one, which is the dimming of a star by its planet. So this is analogous to that we see a small dimming of the sun when Venus passes in front of it. So when we're observing a star and we see a planet going in front of it, and we will see a small dimming of the light coming from that star. And now, the bigger the planet is, the more of a dimming you will see. The longer it takes for the planet to pass in front of the star, the longer of a dimming you will see. So this is a very straightforward method, and it's going to tell you two things in a very straightforward way. One is the size of the planet, and the other one is the orbit of the planet, because we can relate the length of the dimming event to the length of the orbit, and then Kepler's laws helps us out to tell us what the radius of that orbit is. So this has been very powerful, but if we actually want to say what the density of these planets are, we also need a constraint on the mass, and for that we use other techniques that I'd be happy to talk about if you're interested. But this is how the planets are discovered. And if we look at this Trappist 1 system that I showed at the very beginning, these are the discovery light curves of these planets. So you see these 7 beautiful dimmings happening around this star, and you see that they come with different depths, and that is because the planets have different radii. And you see that the planets that are further out, they have a longer dimming event because they're moving more slowly because of Kepler's laws. Now, what was really caught people, I think the word's imagination with this system, is that 3 of these planets are sitting at a very good place, at a very good distance away from the central star, if we want them to be habitable. So what's shown in the cartoon to your right is that the 3 planets that are sitting close to their star, they're too hot to be able to sustain liquid water on their surface. It would boil away. The 2 planets that are furthest out, they're too cold, so any water there, even with the best possible atmosphere, would be frozen out, and you would not have the liquid water that we define as a habitable criterion. But 3 of them are sitting right where we would like them to be. And this concept of the habitable zone is something that is very frequently used in astronomy to look at planets. And it's again shown here. So these are the planets, the EFGs, that are sitting in this green, nice habitable zone where water could be liquid. Because this is such a tiny star, these orbits are all well within the orbit of Mercury in our own system. So if we wanted to find a habitable planet around this kind of M-dwarf, we're looking at planets that are sitting very close to their stars. If we're looking for habitable planets around stars like our own sun, maybe we're looking roughly where the Earth is sitting. And if we're looking for habitable planets around the more massive stars, we're going to move out to something like the orbit of Jupiter, maybe, to find those kind of planets. But here, around an M-dwarf, they're all sitting very, very close in. Now, this gives some extra advantages when we in the future, for sure, want to see what's going on in the atmospheres of these planets. When we're thinking about going from defining some basic criteria for habitability to actually checking whether these planets are inhabited, the way it's going to happen is by looking at the atmospheric composition of these planets, taking very careful spectra of that, and then figuring out if that atmospheric composition can be explained by non-biotic chemistry, or whether there's something that is off about it. And of course, it's going to be much easier to tell whether something is off or not if we have 2 things. One is a big statistical example, so we can see if there are outliers or not. Now, whether the outliers are the life-containing or the one without life, we don't know yet. And the second thing we need to understand is how these planets start out. So what kind of chemical composition do they start out with? And that's where I'm going to be spending actually most of the next 15, 20 minutes on, is what these planets start out like. But before then, I want to talk a bit more about this habitable zone, which I've so far just given you as, on authority as a good way to look for planets that could potentially sustain life. It might seem terribly Earth-centric to demand that a habitable planet looks something like the Earth. That is a rocky planet that's sitting at a distance from the star where you can sustain liquid water. I mean, it does sound like we're not really thinking outside of the box very much, right? So what I want to try to convince you is that it is not that we haven't thought about the alternatives, but that there are some good reasons why we have ended up with this as a good at least initial criterion to look for habitable planets and eventually inhabited planets. Now, we don't know exactly how life originated here on Earth, but we think to have life originate on a planet, you need to have a very rich organic chemistry happening first. Now, why organic, you might ask? Well, carbon is an incredibly common element in the universe, and more importantly, it is an element that can form the largest varieties of bonds, so stable chemical bonds. So it's just so much easier to form a rich chemistry based on carbon than any other atom. And this is actually reflected if we just look at the chemistry that's happening in around young stars in the galaxy. So you might not have realized that, but the galaxy is full of chemistry. It's not just physics. When we look towards, so my basic degree is in chemistry, so I feel passionately about this. But there are these atoms that we heard about in the earlier talk, they don't need a planet to start recombining into molecules. That happens already out in the galaxy in regions that are shielded from the worst of the radiation in the galaxy. And when we look at what kind of molecules we find out in space, well, we don't find as many as here on Earth. We find about 200 or so. And of those, about 80 to 90% are organic in nature. So it seems like nature itself is picking organic chemistry as the favored path towards building chemical complexity. Now, if we want to have a rich chemistry, we want to concentrate reactive material basically into beakers where they can develop into in an interesting way. To do that, it is very bad if you have an ocean and if that's all you have. Then whenever you start forming something interesting, it will get diluted into lots of uninteresting things. So what's much better if you want to build up chemical complexity is to have lakes or ponds or something where you can concentrate things together. So we think it's important to have a rocky surface rather than an ocean, or at least it should make it easier if you have a rocky surface rather than a complete ocean planet. Now, the second thing you might ask is, why water? Why are we focusing so much on water, right? This is actually not coming from the fact that here on Earth, all biology is based on water or need water in one way or another, even though there are some that seem to need very, very little of it. This is a chemical consideration, that water is just by far the most versatile solvent that we know of. So if you want to be able to dissolve the most different kinds of chemicals or a different organic material into a single solvent, water is the one we think should work the best. Now, this does not mean that there is no way that you couldn't think about life developing in other environments or like disregarding at least one of these criteria. But if we have to choose a small number of planets to follow up and characterize more deeply, we're going to pick the ones where we think is the highest likelihood. And as I said, I think we have pretty good reasons to focus on these sort of rocky planets that are sitting in the habitable zone where they could contain water. Now, with all that said, just because you're sitting here at the right temperature, where you could sustain liquid water, that doesn't mean that you automatically have water given to you. So if we want to talk about actual habitable planets, what I want to do in the rest of the talk is move away from this pure sort of minimalist physical habitability and talk about what the likelihood is that these planets are actually habitable from a chemical point of view. That is, that they have access to this water that we defined this habitable zone based on, and that they have access to organic material, which was the reason we needed the water in the beginning. So, so this is an artist's impression of what's some alien sitting on Trappist 1D, I think, if I'm counting the planets right, 1E maybe, is what the view of this alien would be as it's looking towards its faint sun. And I mean, what's very obvious there is the water, that we're imagining that this is a planet that has water. So what is the likelihood that planets form with water? I mean, we have water here, so it's not zero, but what is the likelihood that planets form with water? I think it's the next reasonable question to ask. Well, to answer that, I'm going to have to teach you some basics on how stars and planets form. And this is actually the whole reason that I'm standing down here rather than being up on the podium, is that I want to be able to go up here and sort of walk you through the different steps. So between stars, this space is not empty. I mean, we heard in the previous talk that if in the whole universe, there it's pretty empty. It was at like 1 atom per cubic meter. I mean, that is empty. But if we look in the galaxy, it is not that empty at all. It's many orders of magnitude less empty than that, which is, the bar is not very high, but but it's better. We're talking something closer to 1 atom per cubic centimeter, maybe, which is still doesn't sound too good, but it's better. What's even better from a star formation point of view is that, this one has been blocked out because apparently I forgot to animate something. But what's even better is that this material is not spread out uniformly. Just as galaxies are overdensities in the universe, within the galaxy we'd have overdensities of material, not just in stars, but also in between stars. So we have what we call clouds of material. So these are simply overdensities, where instead of having 1 atom per cubic centimeter, you have like 10,000 atoms per cubic centimeter. And once you start getting to those densities, which are still below the vacuum that we can achieve here on Earth, but once you're starting to get to those densities, and you get that within big enough volume, the gravity, the self-gravity of these systems will cause them to start to collapse. Now, as you're collapsing these clouds, you're releasing gravitational energy. That energy has to go somewhere. Where some of that energy is going is to heating up the center of this collapsing cloud. As it's heating up, it will first just heat up to a few hundred Kelvin, and then we can start observe it with telescopes because it's emitting infrared emission that we can pick up. As it continues to collapse and condense into smaller and smaller and more star-like dimensions, you will get to higher and higher temperatures. Eventually, you will get to high enough temperatures that you can start fusion of hydrogen into helium, and you have your star. So what's shown here is some sort of intermediate step. The first step is hidden behind this here, but the intermediate step is shown here, which is when you have formed your central star and you're still collapsing cloud material on top of it. Now, one of the things that happens during this process is that you form a disk. You form a disk because these initial clouds, they always have some slight rotation. Part of it is that our galaxy is rotating, so it's imparting some angular momentum, but you always have some slight rotation. And this rotation or this angular momentum has to be conserved. To conserve that, you could do it in basically 2 different ways. One is you could, just as you're collapsing your cloud into a smaller and smaller ball of gas, you could speed up the rotation of that ball of gas. But it turns out if you put all the angular momentum into that ball of gas that's turning into a star, you would rip it apart. There's just too much initial angular momentum in these systems. So instead what nature does is that it takes a small fraction of the initial material and it spreads it out in a disk. So an analogy that's typically used is a figure skater who, to slow down the spin, basically stretches out the leg, or to speed up, puts the leg back in. And it's a similar thing that's happening here. So you form a disk to conserve angular momentum. This disk, which is shown here in a blown up version, is where planets form. So planets form from the material in this disk, which basically is leftover gas and dust that did not end up in the star. And eventually, as the planets secrete this material, they go from this disk, which we can observe, and this is super cool, and I'll show you some images in a bit. But we go from this disk to a mature planetary system. Now, what we cannot do yet is look at that planetary system outside of our own solar system and say how often you have water in an Earth-like planet. But what we might be able to do is to say how often they're formed in a water-rich environment. And how we might be able to do it is by looking at what the material here is made of. So the material that actually goes into planets. So we tried doing that, and it turns out to be really, really hard for some technical reasons. So that was I think that was the most straightforward idea, is to really go and look for water in this stage that's just preceding the planetary stage. So we had to go one step back and see how often do you have water in this stage, with the idea that, well, this material will go into the disk, which will go into the planets. And when we turn our telescopes towards that earlier, it's called a protostellar stage, because it's not yet a star, it's a star that's in formation. And we do spectroscopy towards these systems. We do infrared spectroscopy. We see spectra such as these, which is showing the wavelength on the x-axis and the brightness on the y-axis. What is important is that we can identify what some of these dips are. And some of these dips, they're due to things like water, they're due to things like methanol, methane, and carbon dioxide. In other parts of the infrared spectra, we also see that there's carbon monoxide. So first of all, we know that in this early stage, we have lots of water. Water is, in fact, something like the third most common molecule at these early stages of star formation. So if all that water survives and ends up in planets, then planets should in general form water-rich. So what can we say about the likelihood that this water actually survives this pretty long and dramatic journey from the molecular cloud into planets? Well, actually quite a lot by looking at our own solar system. And especially by looking at one particular body in our own solar system, which is that of comets. So if we look in comets, and we look at what the water looks like in comets. So comets are rich in water. They're roughly 50% water, 50% rock is what they look like. So if we look at water in comets, we can look at, there are two different kinds of water. There is normal water and heavy water that we can detect in comets. They have different spectroscopic signatures, so we can tell them apart. So if we look at the ratio of the heavy water to the normal water in comets, what we find is that it's very high. It is far higher than what you would expect if nature didn't care about whether you were forming heavy water or normal water. This is something that we can use as a clue to where this water came from, and specifically whether it formed in the comet, formed in the disk, or survived this long journey all the way from the molecular cloud. Now, the reason we can do that, and this is like my one chemistry slide, so bear with me, all physicists. I know this is something that for many of you seem more complicated than actually it is, so I will try to walk through it. So the reason that this D to H ratio in water is something that we can use as a chemical clue of the origin of water is that as far as we understand, there's only a very specific way to enrich the water in deuterium in space. And it's going through this pathway. So normally, the main reservoir of deuterium in molecular clouds is HD. So it's just an H2 molecule where you have replaced one of the hydrogen with deuterium. Now, if you want to put that deuterium into other molecules, you need to get it ionized. Because as it turns out, all the chemistry in space basically has this ionization step to it. It's basically because it has very low barriers to have reactions with ions. So what you want to do is to add a proton to this HD to make it reactive and make it participate in the chemistry. You do that by having a reaction with H3+, which is the most common ion in molecular clouds, and then you form H2D+. Now you can have the backward reaction happening where you would just have an H2D plus react with an H2 molecule to form H3 plus. And if that happened with the same speeds, then you would have no enrichment in deuterium, and you would not see this enhanced deuterated water signal. However, because of some really cool and basic physics, nature does prefer forming the H2D plus over the H3 plus. And it prefers it, and because the zero level energy of these two molecules is different. So all molecules vibrate at their lowest energy state. And if you have a heavier molecule that's otherwise the same, it will vibrate with a lower frequency and therefore sit at a lower energy. And because of that, nature actually prefers forming H2D plus over H3 plus. But this preference is only important at very low temperatures because this energy difference is very small. But if you're at a low temperature, you'll form this H2D plus in excess. We see it in space, so we know it's from using spectroscopy. Once you have that one, you can put that deuterium in a bunch of different molecules, but most importantly, you can put it into water as water is forming on interstellar grains. So really the main message that I just want to get through is that we understand how we enrich water. And to have this enrichment happen, you need two ingredients. You need low temperatures, and you need to have ions. We know we have this in clouds. So we know this can form in clouds and in protostars. And in fact, if we compare the D to H ratio that we find in the solar system, so this is just showing that this is where it would sit if it was no enrichment. And in the solar system, when we look for water, whether it's in comets or on Earth, we always see this enrichment in D to H. We also see this enrichment when we look in space. So we know this enrichment is happening. Now, this means that it's consistent with being inherited from this early cloud stage. However, which is a very recent realization, is that it's not just consistent, but it's the only way. Because this pathway that I just showed you, it doesn't work at the disk stage or in the comet stage itself. It only works in this early cloud and protostellar stage. So what we can say based on these measurements, and especially by comparing comets in our solar system and protostars, or clouds, interstellar clouds, is that the water in the solar system was inherited from much earlier stages. It was inherited from this cloud stage. So that's conclusion one. Conclusion two, which we had from observations, is that at the cloud stage, water is always present. It's really one of the most common molecules we see. So if we put those two together, a reasonable conclusion would be that planets in general inherit water from their earlier star-forming stages, and therefore that planets generally form in water-rich environments. I think that is something that's become actually that we're quite confident about. So that means that of these two chemical habitability criteria that are put up, so one was the water, the other was the access to organics, at least the water does not seem to be a big issue. We would expect these habitable zone planets to have water on them. But the second thing is then the organic chemistry. And one way you could phrase that is that how special is the very rich organic chemistry that we have in the solar system compared to what we would expect to see on other planets. Now, we know that organic chemistry is rich, not because, or that it was rich when the Earth formed, not because of the Earth today, because we are totally polluted by biology and it's impossible to say anything interesting about the chemistry. But we know it because we can look at what's going on in comets, which have preserved what the chemistry looked at originally in the solar system. And if we look at comets such as Hale-Bopp, what we see is that, well, we have all this water that I talked about, and we have CO and CO2 and other inorganics, but then we have a lot of these small volatile organic species. And these small organics, things like methane, methanol, cyanides, they're there in a very high abundance. And of all these molecules, what researchers looking into origins of life chemistry is especially excited about is the presence of cyanides. These are obviously not very good for life as we know it, but they are very good if you want to kickstart a rich, complex organic chemistry because of the same reason, basically. They're extremely reactive. So we have all of those kinds of molecules. We know they were present in the early solar system. So then the question is, do we expect planets in the habitable zone to also have the same kind of chemical richness? Now you might think that we could play the same game here as we did with water. Just as water is abundant in clouds, so are molecules like methanol and formaldehyde, some of these other volatile organics. And we also see that these organic molecules, when we measure them in comets, especially cyanides, have the same kind of enrichment in D2H. So maybe we could play the same game and just say that, well, if we inherited all our organics, therefore other planets must inherit organics as well. Unfortunately, it doesn't work. For water, this D2H ratio is very diagnostic of where they formed. For organics, they are not. They, as it turns out, can build up this deuterium enrichment through many different pathways, some of which might have happened in our disk. So we actually don't know when it comes to the organics that we find in comets, whether they were inherited or not, and therefore whether they require a special environment, like whether our disk was special in some way or not. So what we need to do, when we can't look at, well, we can't say it was for sure inherited from this earlier stage. What we need to do is actually go and look at the disks where planets are forming right now and see what the organics in those are. And here I just want to pause and give you an idea why this is unfolding right now. Because we have an amazing new set of eyes on the sky, which is called ALMA. So ALMA is a millimeter telescope, or a combination of telescopes done in the Atacama Desert in Chile, which is allowing us to take basically chemical pictures of the disks where planets are assembling right now. Now, what's shown here is what we had to deal with before we had ALMA. So there are two images to your left that's showing what we used to use to constrain the structure of these disks where planets are forming. And then there are two very crappy chemical images of disks in a couple of molecules. So this is pre-ALMA. Now, for the structure, we are going from these blobs to these beautiful ringed structures where we think that these gaps that you're seeing here are due to planets. That what we're seeing here are planets assembling in their disks. When we look for specific molecules in some of these same disks, we also see these beautiful patterns that's really showing that the chemistry in these disks, it differs from disk to disk, and it varies across the disks. So a planet forming far out, away from their star, might end up with a very different chemical composition compared to a planet that's forming close to their star. But what I want to focus on is this particular question of cyanides and what we can say about whether there's an active organic chemistry unfolding in these disks or whether things are mostly inherited. And we can say for sure that it is not mostly inherited. And the reason we can do that, so this shows chemical images towards 6 disks of 4 different molecules. 2 of them have deuterium in them, and 2 of them do not. Now, if things were purely inherited, if things were purely inherited, we would expect a molecule that only has the difference in this where it has a hydrogen or deuterium, that they would behave the same way. They should sublimate at the same place, they should be destroyed at the same place, they should have the same emission patterns around their stars. But instead what we see if we compare in the same disks, this deuterated and non-deuterated molecule, is that we see very different patterns. And that alone is telling us that the chemistry is unfolding right now in these disks. So that means that we really need to understand this chemistry if we're going to understand what kind of chemical compositions planets end up with. Luckily, we can do this. We can go and directly see how much cyanides, how much formaldehyde do you have in these disks on average. We managed to find the slightly more complex cyanide, methyl cyanide, just a couple of years ago, and we're following up on this with other molecules. But the emerging picture that we're finding is that these disks are on average very rich in organic molecules. And they're rich in the same kind of organic molecules that we see here on see in comets here in the solar system. In fact, if we were to compare the kind of organic composition that we now, for the first time, can study in these disks around other stars, we see something that looks almost exactly like what we see in an evaporating comet. What this is suggestive of, even though the sample so far is very small, what this is suggestive of is that the prebiotic chemical conditions that were typical for the young solar system are not rare. We can't yet say how typical they are. The sample is just too small. But what we can say for sure is that we're not that special when it comes from a chemical point of view. So to pull this together, where are we? Well, what we are seeing now from things like Kepler mission and from ground-based telescopes, from the amazing Trappist discovery, which is showing us these habitable planets in our own backyard, is that there are many planets out there that are habitable from a very minimalistic point of view. That is that they are rocky, they're sitting at the distance from their star where you can have liquid water. Roughly 10 to 20% of the stars in the galaxy have such a planet. The second thing that we can say is that a large portion of them, and with large I mean that we're talking tens of percent just from the sample we have so far, of those planets are formed in environments that are rich in water and are rich in organics. There is a big caveat to that statement, though, which I hope that we're going to be able to remove in the next year or two, which is that so far, all the disks that we have studied are disks around stars like our sun. But I just told you that most of the habitable planets are around stars that are much smaller than the sun. And we're not yet sure that the chemistry will be the same around these smaller stars compared to our stars. We have a proposal in to try to test this in the next year or so. So this is something we know how to solve, but it is not yet a closed question. We do not know if any of them are inhabited. And I think that is important to keep in mind. And that is even in the most basic sense, right? Whether they have bacterial life or like any life at all. And the biggest unknown there is really that while it seems like in a rather minimalistic sense, the conditions that were present at the early Earth are, if not common, at least not rare, we don't know if those minimalistic conditions are sufficient for life to originate. There are some really cool work going on trying to understand what kind of chemistry could have led to the origins of life on Earth, but we're still pretty far off from any kind of conclusion when it comes to that. And so this is, I still think this is a scientific question that hopefully will be resolved, but it is far from resolved right now. And as I said at the very beginning, I think one of the things, while we're trying to figure out what these exoplanets are made of, I think we should absolutely go to Enceladus and other places in the solar system and see if we can just find out one more data point to see. That would help so much in trying to understand what are the actual sufficient conditions for life to originate. But I don't really want to end there. Instead, I want to spend another minute or so thinking about going back to the questions in the second slide on what this is telling us about what kind of universe we're inhabiting, and therefore about the creator, if anything. And I think there are two things that come up here. One is really what it's telling us about how God creates, so about creation as a whole. And the second thing that it might tell us something about is our relation, like the privilege, if it is a privileged relationship between man and God that seems to come out of our scriptural understanding. So two things. Now, as I said at the beginning, there is a difference, I think, in how we understand creation if it is that we are, one of many words, if we live in a universe that's really teeming with life, that might be even teeming, if not teeming in the same degree, with rational life. There is a difference to that if we look up at the stars, and it seems like every star in some sense is there to sustain a world, whether if we are sort of a lonely ark sailing through the universe in a rather beautiful and vast and immense space, but rather cold in comparison to a universe which is full of habitable worlds. If there is rational creatures on these other worlds, I think there is obviously some need to think about what that means theologically. And I'm not going to pretend that I have thought about it in any depth. I'm not a theologian, so this is more my urge that there is, I think, a sense of that we need to look over our theology of creation, at least of this theology of how man relates to God and God relates to man in a privileged way. I'm not too worried about that this will disrupt our relationship with God. What I'm showing here on this, what I like this figure here to the left, is that it's showing the angels visiting Abraham. I mean, there are extraterrestrial, non-human, rational beings already in our tradition, right? I mean, this should not be something that is really upsetting our relationship to God. I would be super excited to whether if we found whether there were rational beings elsewhere in the universe. But I think it would ask some important questions, and especially on whether they fell. I mean, C.S. Lewis has this beautiful little space trilogy where he goes and visits the Martians who did not fall. And there's this beautiful poetry to that I think sometimes we should be thinking about, where they have not fallen and therefore in some sense have a closeness to God that we do not. But they still look with a longing and amazement towards Earth, where the Creator stepped into creation. And I think there's definitely food for thought there when we are thinking about how this exoplanet research relates back into the faith that we share. So where I want to wrap up is that we are, in the next decade or so, we will have a good enough characterization of a sample of exoplanets to know whether they have oxygen, for example, in their atmosphere. We will start to have the first ideas on whether atmospheres around these habitable zone planets, whether they look like they could just be explained by normal chemistry, abiotic chemistry, or whether they're starting to hint at something else. And I think we should come there prepared. So this is just my urging to the theologians to take over and ask questions and help allow us to help informing you. And with that, thank you, and happy to take any questions.